right, let's see here. So today we're starting Chapter 8. We'll finish Chapter 8 by Friday. Monday we'll review. Next Wednesday is our test. So there's mastering homework tonight. Wednesday night we'll do a quiz today, quiz Friday, homework next Monday. And then we're set to start talking about something else. Let's see here. All right, so where we left off on Friday, we were talking about how electrons have specific orientations, right? They have a spin number, they have an angular momentum number, they have a magnetic, or angular momentum, magnetic quantum number, magnetic spin number, and all those give an individual electron within the atom a certain spot in the atom to be found. So how does this tell us about the periodic table? Well, we'll back up a little bit and talk about, in general, the periodic table and the periodic law. So the modern periodic table is credited to Dmitri Mendeleev, and he based his description of the periodic table on the periodic law, which we had in class a few days ago. I don't remember exactly when. But the periodic law states when elements are arranged with increasing mass, the properties occur periodically. So our current periodic table is arranged with increasing atomic number, because that's slightly more accurate than the increasing mass. In general, the masses do increase left to right, so it's going up, 50, 51. But then we get some weird things like in the middle, like manganese has a similar mass to iron, really close to cobalt, so we get some, I think cobalt's actually heavier than nickel. So using atomic masses, they wouldn't line up correctly, but using the atomic number, we get a better arrangement. So the current periodic table is arranged based on increasing atomic number, which is a measure of what? Like, what's the atomic number tell you about the element? Number of protons. So if I know the number of protons, what do I also know about the element? Number of electrons. And so if I know the number of electrons, then I know in general how they should be arranged. Periodic table actually tells me a lot about the quantum mechanical theory and how I can find where an electron is. So let's talk about electron configurations and how we know that. So all of Chapter 7, we work through quantum mechanical theory, very baby quantum mechanical theory. But in general, it describes the behavior of electrons in an atom. So since a covalent bond is sharing of electrons, quantum mechanical theory helps us understand when a chemical bond will be formed. So in order to do this, we have to have a way of describing where an electron can be found in an orbital. So an electron configuration for an atom. Shows which orbitals have electrons in an atom. All right, so if I'm describing an orbital, how many of the quantum numbers do you have to know? One of them, two of them, three of them? You know at least three. Orbital means you have to know the N and the M and the L and the M sub L. You have to know all three in order to tell me about the orbital. So let's look at, we'll go easy, we'll look at hydrogen. All right, so if hydrogen has atomic number 1, how many protons does it have? 1 proton. If it's neutral, then how many electrons? If its mass is 1, how many neutrons? 0. So 1 proton, 1 electron, 0 neutrons. So if it has just 1 electron, what is the lowest value of N that's going to exist in? N equals what? What's the lowest energy number for N? 1, right? The lowest number value for N is 0. All right, so if I have a value of 1 for N, and I want to know about its orbital, what's the next thing I have to tell you about it? And then L. So what does L have to equal? 0. And I still want to know about the orbital, so what's the one thing I'm missing? M sub L. And what's the value of M sub L? 0. All right, so that's the lowest possible energy configuration, right? Lowest N. If N equals 1, then L has to be 0. M sub L has to equal 0. I now want to write this in shorthand. I want to write in shorthand. So, right, I use the number value to tell you about that. If L equals 0, what's the letter I give that? S. How many electrons am I referring to in this particular example? 1. So I give it a superscript 1. So the N tells me this. The L tells me the letter. And this number superscript 1 right here tells me the number of electrons. How many possible electrons can you put in an orbital? In a single orbital, right? 2. So if I wanted to know one more piece of information, I would ask about the M sub S. What's a possible value of the M sub S? Right, half. Either plus or minus 1/2. That'd be good. All right, so that is shorthand, and that is an electron configuration. What color did I not use? All right, so when I say electron configuration, I now mean, so if I say, give me the electron configuration for helium, I mean, give me the shorthand. I don't need all this information. You're going to condense it for me into a little shorthand. We'll do lots more, but. Actually, let's do one more. Let's do one more just for practice. Let's do. No, just kidding. My example's far ahead. Let's do this first, and then we'll come back to it. So I have to do electron spin first. All right, so electron configurations, which is the shorthand we just did, right? That is the shorthand. Can also be represented in a orbital diagram, where an orbital diagram is a figure. So it's a drawing of sorts. In a orbital diagram, you give every orbital a box. So I would say, this is my 1s box. How many electrons live, for that example of hydrogen, we had 1 electron. And I'm going to represent that 1 electron visually by giving it an arrow. For whatever reason, they chose half arrows. I guess because it's a half, right? Because that's showing me spin direction, and m sub s is a half, so it's an up half. So again, the number 1 tells me the n. This tells me n. This s tells me L. The fact there's 1 electron and it's up tells me both m sub L and m sub s. So I get all the information. So in my orbital box diagram, the direction of the arrow shows the electron spin, which is our m sub s. But like we talked about on Friday with the Pauli exclusion principle, each electron in an atom has a unique set of 4 quantum numbers. So if I have this electron with a spin up 1/2, there's no other electrons in that atom that have spin up 1/2. Which, when we get to, right, this is fine if it's just 1 electron. What if now I have helium? We'll scoot over one. So helium. Helium has an atomic number of 2, so how many protons does it have? Okay, so if it's neutral, then how many electrons? Also 2. It has a mass of 4, so how many neutrons? Okay. All right, so now I have 2 electrons. And we have to write out the 4 quantum numbers for each electron. Right, because they can't have the same. So they each have to have their own set of 4. So if I look at electron number 1 versus electron number 2, let's do number 1 first. What's the lowest energy n it could have? What's the lowest number value for n? Seems like I'm asking a lot of questions over and over again. Yeah, 1. It's on purpose. All right, so we already said if n equals 1, then L equals 0, that m sub L equals 0, and m sub s plus 1/2. All right, so then what would be the 4 quantum numbers for the second electron? Does it have to change energy levels? No, it doesn't, because it can be the other half of the spin. All right, so now I have 1 orbital with 2 electrons in it, 1 going up, 1 going down. So if I want, so this guy over here is hydrogen. If I wanted to draw an orbital diagram for helium, his box would start off looking the same, right? Because the first 3 quantum numbers are identical. This first electron looks just like the one that was in hydrogen, but now it has 2 electrons spinning in opposite directions. So all these tell me the same amount of information. I can either write out all of it, or I can draw it as a box. What if I wanted to write it in shorthand? Right, I would do 1s, and how many electrons am I referring to? 2. So I'd give it a superscript 2. So all of this plus all of this are all interchangeable. They all tell me the same information. You can see that there's some advantages to writing out the shorthand as for writing out the 4 quantum numbers for every single electron, because it's fine if I only have 2. But in a second here, we're going to move to electron configurations, they have like 20 electrons. You're not going to want to write out all 4 quantum numbers for every single electron. So the shorthand comes in handy. Okay, good so far? Okay. Then just here is a nicer visual of the stuff I just had in the previous one. All right, so the number tells you N, angular momentum L tells you about S, and the electrons in the orbital or subshell 4. So this one is the electron configuration. And then this one's the orbital diagram. So when I ask for one or the other, I'm either looking for a picture or I'm looking for a drawing, or a picture or a shorthand. All right, we ready for more than 2 electrons? I feel like we are. I think we're ready. All right, so the 2 we just looked at, hydrogen and helium, the energy over the orbital, right, only depended on the principal quantum number n. And again, that should be a script E, L. For atoms with more than 2 electrons, the energy depends on L and N. Right, because N is the value of L depends on what value of N you had. Let's see if I have this on. Okay. Somehow my notes are out of order. Yeah, let me see. Okay. Sorry, pause a second. Somehow my sheets are out of order. I'm not sure. Okay. All right, so the question is, how do we see this? And it goes back to that figure we had over here that looked like, all right, this was energy, and this is, there's no label really for the Y. This is N equals 1, right? Then we'd have N equals 2. All right, so if this is my energy diagram, for just hydrogen and helium, N equaled 1 because it was just the lowest energy. If I have now N equals 2, what are my options for L now?
1 and 2.
It really means and, it doesn't mean or. So if I'm in the second energy level, it means I have L equals 0 and I have L equal 1 available to me. So I can still put electrons in the low energy, and I'm going to put it up here. So it seems like we're always talking about, so far, like looking at just one level at a time. But if I'm in an N equals 2 energy level, it means I must also have N equals 1. You can't bypass a level. So they always build up bottom and the top. So I have to have electrons in N equals 1. I'm also going to put some electrons in N equals 2. So let's take a look at how we build up some multi-electron compounds. So let's do the shorthand notation, the electron configuration for lithium. Looking at lithium, how many electrons should lithium have? 3, right? If it's atomic number 3, it should have 3 electrons. All right, they always start this way. We always start with n equals 1, lowest value of L. How many electrons can I put into this orbital? 2. Okay, I've now filled up my n equals 0, L equals 0, n equals 1, L equals 0 level. What n value then comes next? Okay, if n equals 2. So then what's the lowest L value that we could use? 0. We're going to use 0 first. So if L equals 0, then what letter do I give that? S. How many electrons do I have left over? 1. All right, I think we're ready to go tricky. We're going to do magnesium. Feeling confident. You guys can go all up to 12. All right, so magnesium has 12 electrons. Actually, you know what? We're not ready yet. Let's do this first. Yeah, no, let's do this first. Sorry, I'll come back to that. Let's do this first. Go into your next slide. We don't have enough platforms yet, so this will make more sense in a minute. When I printed them out, my notes got shuffled up with my PowerPoints. They're not in the right order. All right, so now we know that the energy of the orbitals, right, which is the n value. We can now build up the ground state configurations for other elements. We have to use something called the Aufbau principle. The Aufbau principle forces us, that's us, to add electrons from lowest energy to highest energy. So, which is what we did with lithium, right? We did the lowest value of N, then we did the next value of N with the lowest value of L. So, let's do carbon. So if I look at carbon, it has 6 electrons. And I'm going to use an orbital diagram rather than the shorthand, because it'll make more sense if I do it as a picture first. And because I'm lazy, I don't write boxes, I just write platforms. Your choice if you prefer the boxes or the platforms. It's just my boxes start to get kind of wonky looking. And so it's just safer if I just do lines. All right, so here I have my 1s. How many electrons can be in the 1s orbital? 2, right? How many electrons do I have left to place? I got 4 more. All right, so what orbital comes next? 2s. And how many electrons can I put in the 2s? 2. All right, I'm still in n equals 2, and I've used up L equals 0. So if I have L equal 1, what letter does that get? P. How many orientations does P have? 3. 3 orientations. So it gets 3 platforms, or 3 boxes. Because if L equals 1, right now I have M sub L equal -1, 0, +1. So 3 orientations, so 3 different places I could put those electrons. How many electrons do I have left to place? 2 left. We now use Hund's rule. to tell us where to put them. So degenerate orbitals means orbitals with same N and L value. So this 2p platform, right, there's 3 of them. They're all going to be the same energy. They're degenerate to each other. They all have the same energy. They're all equal to each other. So we will, in these cases, right, there's only one platform, so we put 2 on one platform. Hund's rule says an electron would prefer to have a platform to itself. So if possible, put only one in, and then put another one someplace else. And then when you run out of platforms, come back and fill them back in. So there's 2 left. So it looks like that. All right, now we're ready for magnesium. All right, so now we have 12 electrons. So what platform do I use first? Always 1s. How many electrons can be in the 1s orbital? 2. All right, I got 10 left. All right, so now I got 2s. How many can go into the 2s? 2. All right, what's my other value if n equals 2? L equals P, right, we got P, so L equals 1, got 2P. So let's see, I've used up 4, I still have 8 to go. So 1, 2, 3, 4, 5, 6. Am I done? No. What, can I put any more anything in n equal 2? Now I'm all out, so now what? I gotta go to n equals 3. So if n equals 3, what's the lowest value of L I could have? 0. If L equals 0, then what letter is that? S. And how many electrons can go in there? 2. And that should be 12. Good so far? You may have done this something like this. Yeah.
So would we write that in shorthand?
Mm-hmm. Yeah. That was going to be my next, yeah, no. So now I'm going to change this. This is orbital diagrams. I now want to write it as electron configurations. And I'll show you a third shorthand way to do it. All right, so shorthand would be 1s2, 2s2, 2p6, 3s2, where the superscript tells you how many electrons you put in that orbital. So they tell you, in some ways, the orbital diagram tells you more information because it tells you about the m sub L, where this doesn't tell you as much information, which is fine. All right, let's look at chlorine. So chlorine's number 17, so how many protons do I need to put in there? 17, good. So it needs 17 electrons. How is it related to magnesium? Is it in the same row? Yes, so it should have at least that many electrons. And it's going to be same starter electron configuration. So if we know magnesium, we know at least the first 12. We know for sure that's going to look like this. These are the first 12. Okay, so how many more electrons do I need for this to be chlorine? 5. I know everybody's drawing. Very good. Okay. if I need 5 more, what can I put some more in the n equals 3? I can, but what letter do I have to give it? P. So I need to put 5 more in there. So I'll do 1, 2, 3, 4, 5. So everybody has a drawing that looks similar to that, right? So now the question is, can I extract from that, bless you, what the 4 quantum numbers are for this electron? What would be the n value for that electron? It's the last one I drew. So what would be the n value for that electron? 3. What's the L value for that particular electron? If it's in a P. Yep, it's 1. Okay. The last 2 you're kind of flexible on. I usually think about it as -1, 0, 1. There's no hard and fast rule about that. So I'm going to say 0 is a possibility. That's fine. It could be. I would accept -1, 0, or +1 because they're not exactly hard and always the same. But if you draw it as a down arrow, what half value do you have to give it? It's -1/2. So that would be a set of 4 possible quantum numbers for that electron, which makes sense, right? It's the only 4 electron numbers it can have for that spot. So now we're ready to talk about the periodic table a little bit. A few minutes of periodic table. Any questions, any of that so far? Okay. There's a figure from your book. It's a little cheat sheet if you want to go back and look again. All right, so boron, right, has 5 electrons. We do always the 1s, then the 2s, and then you add electrons going first across, then adding the other spin. All right, so now we are ready to look at the periodic table. And with our new knowledge of electron configurations, we can pick out pieces of information about the periodic table based on where the element is. So, the highest principal number, what letter is highest principal, or is principal number? N, right? So N. N increases by 1 going down a row. So I don't have a pointer in this classroom. Oh, I do. So if I'm looking at the periodic table over here, this is row number 1, which means all the n's can only be 1. This is row number 2, which means n has to equal 2. N equals 3 for the highest electron, 4, 5, gets a little squirrely. Well, a little crazy down here. But in general, the first few rows are very obvious. 1, 2, 3, 4, 5. And then going up 9, get a little craziness. And as you move across a row, the number of electrons increases by 1. Like we had it here before, right? We had, let's see, we did lithium, so 2s1, and then we looked at carbon, 2s2, 2p2. Then we looked at magnesium, which is all the way up to 3s2. Then chlorine, 3p5. My little caveat to this, the number of electrons increases by 1 in the outermost energy level. But the value of n in the outermost energy level stays constant. Like, if you have the figure, it's a little easier to see. Everybody's at 2 all the way across in this, and everybody's a 3 all the way across this. So while the number of electrons are increasing, the N isn't changing. So what do I mean by the outermost energy level? And how do we know which electrons are in the outermost energy level? So the outermost energy level electrons are the ones found in the highest energy level of the atom. Right, the ones with the greatest N value, they're going to be the ones that are added last. So the outermost energy level electrons are found in the highest N value of the atom. Chemical properties of an element depend greatly on these electrons. These are the electrons involved in bonding. So these outermost electrons are the ones that are farthest away from the nucleus and therefore available to do chemistry with other atoms. So if we look at the example we had, like 2 minutes ago, magnesium. What is the greatest value of N in my magnesium atom? Is it 1, 2, or 3? 3. N equals 3. So these 2 electrons are in the highest energy level. They're the outermost. Those are electrons we're going to call valence electrons. Those electrons they're the ones that the chemical properties depend on, and these are going to be the electrons that are going to be involved in bonding in some way. Those are valence. All the electrons that are not valence are called core. They're necessary in order to keep the charge balance for the atom, but they're not available to do chemistry. So they're needed so that everybody's neutral, but they're being held on the inside, so they can't do chemistry. All right, I'll do one more example, and then I'll let you guys do your quiz. Let me do this example. And I'll show you 3 different ways to write an electron configuration. All right, so let's do, what's a good one? Phosphorus. All right, phosphorus has 15 electrons. So we'll write it in 3 different ways. First, we'll do the one with the platforms. How do I know I should automatically go on out to 3? Where's phosphorus found? First, second, third, fourth row. Third row, it's in the 3rd row, so I automatically know I have to at least have these many platforms available. All right, then we fill it up from the inside to the outside. All right, so that's 2, 4, 6, 8, 10 electrons Do I fill 1 in the 3s and then go on to the 3p and then come back to 3s? No, don't do that. All right, so 2, 4, 6, 8, 10, 12. Okay, 15 electrons. Which value of n is the valence electrons? The 1, the 2, or the 3? 3. So these guys are all valence. All right, so that is the orbital diagram. What if I wanted to do it as an electron configuration? I'd do 1s, and then what exponent should I give it? Superscript 2. What about the 2s? What about the 2p? What about 3s? What about 3p? You can see it's a little bit faster to write that way. What if I want to do it even shorthand? An even faster way to write it is to tell me these guys are the core electrons, right? They never change for this element. How many electrons are here in my core? 10. What element would also have 10 electrons? Neon. As a shorthand, you could just go ahead, they use brackets. And this means to the reader, start with neon. Go ahead and assume 10 electrons. After you get to neon, fill up the 3s, put 3 in the 3p, and you're done. So all 3 of these are acceptable shorthand. If I want one specifically, I will tell you which one specifically I want you to draw out. Good. All right, you will need a calculator or something to calculate on.